I'm Anuradha Mathur. I teach physics at Modern School Vasant Vihar in New Delhi. We have been working on the unit of work per energy, considering the meaning of work, its calculation, meaning of power and its calculation, understanding mechanical energy in its two forms as kinetic energy possessed by moving systems and as potential energy possessed by bodies which are raised up with respect to a certain point and their shapes. We have learnt about springs and its application when they store energy. We have done work energy theorem and its use for real life situation. We have also gone ahead and done a study of elastic collision. It is from there that we are going to use some of the ideas on elastic collision and use them for special cases in this lesson. We are going to study how the equations that we had set up and found in the earlier lesson on elastic collision, how they can be modified in very special cases and can be checked out in real life as well. Before we consider special cases, let us consider what we were doing in our previous lesson. We had a smooth horizontal surface. We had two spherical bodies. One had a mass of m1, the other had a mass of m2. They were both moving in the same direction with initial velocities of u1 and u2, and they finally acquired velocities v1 and v2. And from our equations 7 and 8, if you remember, these velocities could be found in terms of u1 and u2 and the masses m1 and m2. Let us consider a special case. What special case? Let us say special case 1, in which the mass of the two spherical colliding bodies is the same. It is not necessary that their initial speeds are same, and say this value is equal. If you now use this concept or this idea in your equation 7 and 8, you will find that your value of v1 will work out to be equal to u2 and the value of v2 will work out to be equal to u1. That means, there is an exact interchange of velocities that will take place for the two bodies which are equal mass. Now, is it possible? Can it ever happen like that? Just in order to see that it can really be there, you might have seen a toy in which this principle is used, or may have seen any video on YouTube explaining or showing this phenomena. To see that as an example, I have a toy here which I can share with you, and you can see how the velocity exchange takes place. There is a set of 5 balls here suspended by very fine string. If I take one of them and raise it to a certain height, I will give it potential energy. When I let go of it, it is going to have some velocity with which it will strike the next one. Now, the next one is already at rest, and so from our concept, if these were all equal mass, then what will happen? The velocity exchange will take place. So much so that this last one over here is going to acquire the velocity as the first one. That means, it would be knocked off from its position with that velocity. Let us take a look. Watch carefully. I am raising it and leaving. The sound produced here is obviously taking care of the kinetic energy, and some of the kinetic energy being lost, it is not a case of perfectly elastic collision. I show the same thing with 2 balls. This time the mass has increased. So, the initial velocity, let us say, is the same, u1 for both of them is the same, but this time the mass is larger. So, let us see what is going to happen now. Since 2 balls were this side, 2 of them stuck out on the other side. What if we take 3? Keep thinking in your mind what will happen. Watch how momentum conservation allows 3 of them to stick out if there were 3. Obviously, if you take 4 balls, 4 of them will be out, and 5, of course, the question does not arise because there is no collision then. Let us take another special case. This time let us have a very heavy mass being struck by a small one. So, what will it look like? Here is a smooth horizontal surface and a huge mass is sitting here. This is a spherical ball and a tiny one is moving towards. It is hard to imagine it off the ground, but you could, like in the game of pit 2. So, you have mass m1 and moving with the speed u2 and a huge mass m2 with an initial speed of 0. That means, this was not moving, and as this strikes, what will happen to the final velocities of the two? So, on using our equations 7 and 8 from our previous lesson, we can predict the value of V1, which is minus u1, and V2, which is equal to 0, which means this remains stationary, this goes and strikes it and rebounds. This kind of thing can be experienced, or we may have already experienced it, if you take a marble and drop it on a hard floor. What would happen? It will go right down to this point. This is our massive mass, which is stationary, u2 is 0, and this rebounds and goes up. If you were to do this experiment carefully, you might even find that it rises up to the same height. Tennis balls are seen to go like this. They go up to a particular value, come down, go up to a lesser, go down, and this goes on diminishing. Why is this not maintaining the value of the initial velocity? You must have guessed that the sound that it produces here and at this knock and at this knock takes away the kinetic energy, and so the body, though rebounds, loses out on its kinetic energy and therefore does not get the same height which it converts into its potential energy at this point. You can do this experiment with any kind of ball, but make sure you get a smooth surface, say like a granite floor or a cement floor. You can't do this experiment on sand, because then it would just embed here and not bounce back. Another special case can be considered, and in this case we could consider the body which is colliding with the smaller one to be the massive one. So, watch this. This is your small m2 having an initial velocity of say u2. What would happen in this case? Well, again you would use your equation 7 and 8, and this time you will get the value for V2 to be equal to 2 times u1, and you would get the value of V1 to be equal to u1. Interesting, this goes along as if nothing has happened, and this is going to acquire twice as much speed as this one. You can find examples of this type also, especially in games of tennis, in games of your throw ball or volleyball and stuff like that. And you can confirm this result, remembering that it is not going to be 100% true, because it is not going to be a case of elastic collision. Now, when collisions take place, say for example, on a ground or on a floor or on a flat surface, what happens to the striking bodies? They move in the same plane. They may not move along the same line, and that we term as collision in 2 dimensions. I have a tray, there are some marbles here and there is one other. This extra marble I am going to use as the striker. What do you think will happen? These are not going to jump in parabolic paths, but are going to move in this plane. This will be termed as collision in 2 dimensions. The plane over here takes care of that. Are we in a position to talk about what would be the final velocities in this case? Do we need some more values, or can we just predict as we did in the earlier simple straightforward elastic collision case? Let us take a look at that. In order to understand collision in 2 dimension, let us consider a simple diagram, and we have this as the horizontal line. Let us say one of our marbles is placed here, another one is approaching it from this direction. Say this is m1 moving with the initial speed of u2, u1 and u2 for this, u1 for this one, and say after strike it moves in different directions. Say one goes like this and the other, let us take a different angle, goes in this direction. This is say the track of m2, it moves with the speed of v2 making an angle of theta, and this is the track of m1 moving with the speed of v1 making an angle phi. If we were to write the equations for this case and say we consider first their kinetic energy, assume it to be conserved. So, it will be m1 u1 half m1 u1 square plus half m2 u2 square, and this would be equal to half m1 v1 square plus half m2 v2 square. No problem with that. In the other case, you could divide this or resolve these directions into horizontal and vertical components, and let us see what equations we would get that. Momentum along this line for both of them and momentum along the vertical for both of them. So, you will get a pair of equations and they would look like this: m2 v2 cos of this angle cos theta plus m1 v1 cos of phi, and this should be equal to the initial momentum, which would be m1 u1 m2 u2. This equation, if you notice carefully, is taking care of the momentum in the horizontal direction. Likewise, momentum in the vertical direction where it was not existent earlier, final momentum here would be m2 v2 sin theta, which would be equal to m1 v1 sin phi, because the sum of these would be equal to 0. These had no component in the vertical direction. So, these two equations here, these for the momentum and one here. Now, notice you have 4 variables v1, v2, theta and phi, and you have only 3 equations to deal with. Therefore, you must know at least one of them in order to find the others. So, it is slightly different from tackling collision along a straight line, whether vertical or horizontal, as compared to a 2D case. So, in this lesson you have learned using special cases how to find the velocity of colliding systems after collision. You have learned using the toy how your calculations were nearly correct. You have studied and understood how collision in 2 dimension would be taking place. You have learned how to calculate and predict the direction in which colliding systems in 2 dimension would move. After all, that is a very common collision taking place in real life. The game of snooker, billiards are all based on this. Perhaps the players calculate it in their mind and practice towards it, so that they can put the ball in a catch and earn points for themselves. Maybe you could also look around and enjoy the collisions around yourself. Use the simple ideas that you have learnt here while bouncing a ball, while playing with your friends, and use this lesson in every way possible. Thank you.